Hello everyone, this is part 4 of section 14.7, or 15.7, sorry. We finished up last time with some examples of just setting up the volume for regions in cylindrical coordinates when given the graphs. So now we'll look at a couple examples to finish up where we'll actually calculate the volume. And so here we have an example where we have a hemisphere above and the x-plane, y-plane below, and then laterally a cylinder. So for questions like this, I'm going to give you the graphs, but you should practice when you do your homework, of course, to be able to graph these types of things. So off to the side, we'll make a little graph here. And we have the XY plane below, a hemisphere above, and then a cylinder. So let's draw the cylinder shape. So here's a circular base. Notice the radius of the cylinder is 3. And we'll extend that above. Doesn't have to be to scale or anything, but so there's my cylinder. And let me move the z-axis up a little bit. And then we've got a hemisphere on top. So the equation of the cylinder, x squared plus y squared equals 9. And the equation of the hemisphere, z is the square root of 25 minus x squared minus y squared. So I guess the first thing we'll have to do is get the two equations in terms of cylindrical coordinates. And remember that one of the formulas that's often used to convert these equations into cylindrical coordinates is the famous r squared is x squared plus y squared. So for example, the x squared plus y squared equaling 9 cylinder, we can immediately replace x squared plus y squared by r squared, and so therefore the radius is going to be 3, and that's always positive, remember, because the angle determines where it is. So there's the radius, and then for the hemisphere, z is the square root of 25 minus x squared minus y squared. And I think we saw this algebraic move last part of this lecture, where we could factor out a negative from the negative x squared minus y squared, and then replace that by r squared. So we get z is the square root of 25 minus r squared. Okay, so now we'll set up for our volume. And our volume formula, remember, is the triple integral of dz times r dr d theta. And so as we look at how z ranges, basically it starts at 0, so you have to think of these vertical strips, right? And z ranges from 0 to the hemisphere, so 0 to the square root of 25 minus r squared. And then r, if you want to, you don't have to sketch it, you can see it from just looking at the base in the XY plane, but if you wanted to, make a sketch. It's basically a circle with a radius of 3 in the XY plane. So R is going to range from 0 to 3. And then finally, theta is, so we're basically, theta's off the x-axis, remember, and you're basically spinning the entire way around the z-axis. You can see that from the base as well. So keep in mind, if this was a half of this type of object, it would be, depending on, let's say, the front half, then it would be 0 to just to pi, but because it's the whole thing, 0 to 2 pi. Okay, so that's the setup, and now the actual integration. So integral 0 to 2 pi, integral 0 to 3, integrating dz, we get z, and that's evaluated as z goes from 0 to the square root of 25 minus r squared, and then that's times r dr d theta. That's just going to give us the double integral 0 to 2 pi 0 to 3 again. Okay, plug in the upper limit, z, that's the square root, 25 minus r squared, but then it's times r, because the lower limit goes in of a 0 in for z, so that's 0, so then times the remaining factors, r dr d theta. Okay, now to set this up for integration, 0 to 2 pi, integral 0 to 3. Let's bring this r out in front and change the radical to 25 minus r squared to the 1/2. And that's with respect to r, with respect to theta. And at that point, you can see that it's going to require a u substitution. And so, let's see where I want to do my u substitution. If I do, let me do it underneath. U is 25 minus r squared. Du would be minus r squared. Excuse me. Minus 2r dr, modifying minus 1/2 du is r dr. So here's our u to the 1/2, and the r dr represents minus 1/2 du. Okay, so let's bring the negative 1/2 out in front. We've got the integral 0 to 2 pi, integral, I'm going to say a to b, because I'm making the change of variables, u to the 1/2 with respect to u, then with respect to theta. And integrating, there's the negative 1/2, integral 0 to 2 pi, okay, u to the 1/2 integrates to be u to the power 1 greater, 3/2, divided by 3/2, and that's evaluated, again I'm going to say from a to b, and then this is going to be with respect to theta. And let's see, let me try to squeeze it in here. So that'll be invert 3/2, 2/3 times negative 1/2 minus 1/3. Then I get the integral 0 to 2 pi of our u was the 25 minus r squared to the 3/2, and that's evaluated as r goes from 0. So now we go back to the original limit, 0 to 3 was what r was ranging. That's with respect to theta. So that gives minus 1/3 integral 0 to 2 pi, and then put a 3 in. So we get 25 minus 9 is 16 to the 3 halves. And then put a 0 in. Okay, so we've got to be careful here. So upper limit gives 16 to the 3 halves, but then lower limit gives minus 25 to the 3 halves. And that's with respect to theta. And so 16 to the 3 halves, use a calculator if you need to, that's 64, minus 25 to the 3 halves is 125, so that's minus 61. So therefore, we have minus 1/3 integral 0 to 2 pi of minus 61 with respect to theta. So I'll just make that positive 61 over 3, integrate d theta, we get 1 theta, and that's evaluated from 0 to 2 pi. So then upper limit goes in 61/3 times 2 pi. Lower limit goes in, that's a 0, and so we get 122 pi over 3. Okay, so final example. This one I chose to go over because it's really not that difficult, and it's kind of interesting at the end what we could summarize from this. But it's just the volume of a solid, it's just a hemisphere, and bounded below by the xy plane. So that's all that it is a hemisphere at 3, with a radius of 3. So a sphere with a radius of 3, but the top half. So if you considered, let's say, a circular base, maybe a little bit above there. Just remark that as 3, just to make the picture look a little bit prettier. Okay, so all that it is the top half of the sphere, and its equation is x squared plus y squared plus z squared is 9. Okay, and if you wanted the xy plane, it's just going to be a circular base with a radius of 3 as well. So in order to take these vertical strips in the y direction, we need to transform the x squared plus y squared plus z squared equaling 9. So immediately x squared plus y squared is r squared. And we're going to solve for z. So z squared is 9 minus r squared. Formally we should say plus or minus the square root of 9 minus r squared. But let me move up here and say that we're going to take z to be the positive square root of 9 minus r squared. And that's because we're looking for the top half. Okay, so then our volume, triple integral dz r dr d theta, so our standard volume formula in cylindrical coordinates. Okay, z is ranging from 0, the xy plane, to the top half of the sphere, the square root of 9 minus r squared. R is ranging from 0 to 3 again. You can look at the xy plane if you like. R goes from 0 to 3. And looks like X is spinning all the way around again. All the way around the Z-axis. So 0 to 2 pi. Okay, so we integrate dz to get z. We get the integral from 0 to 2 pi. Integral 0 to 3. Again, integrating dz to get z. That says z goes from 0 to the square root of 9 minus r squared. And then we have the r dr d theta. Okay, so that gives us upper limit goes in. And so that is the square root of 9 minus r squared. And when we put the lower limit in, this is almost identical to the last example. And when we put the lower limit in, we get a 0. So let's kind of do a few steps here at once. Kind of skipping this step here basically. I'm just going to write the r in front of, and then that square root of 9 minus r squared will change to the 1/2 power. So knowing from our experience in the last example that we're going to require u substitution again. So here it's 9 minus r squared. So du is negative 2r dr, so negative 1/2 du is r dr. So here's u to the negative 1/2, the r dr represents negative 1/2 du. So that's the integral from 0 to 2 pi. Oops, let's bring that negative 1/2 out in front, right? Maybe that would be an efficient thing to do here. Okay, and then I'm going to do the integral from a to b again. And then my u to the 1/2 with respect to u, then with respect to theta. So that's negative 1/2 integral 0 to 2 pi. U to the 1/2 integrates to u to the 3/2 over 3/2 again. And this is evaluated, again I'll say a to b. Then that's going to be with respect to theta. So now the volume is going to be, there's the 2/3 times the negative 1/2, so negative 1/3, then integral 0 to 2 pi of, now our u was 9 minus r squared, now to the 3/2, and that's evaluated as r goes from 0 to 3. That's with respect to theta. So we get negative 1/3 integral 0 to 2 pi of, when we put a 3 in, we get a 0, because r squared is 9. So we get 0 minus, lower limit goes in, 0, so that would be 9 to the 3/2, and that's with respect to theta. Okay, 9 to the 3/2 is 27, and 27 times negative 3 would be positive 9, so 9 times the integral from 0 to 2 pi of just d theta, which is 9 theta from 0 to 2 pi. Upper limit gives 18 pi, and lower limit gives us 0. So we get 18 pi. Now, the interesting thing I wanted to note here, this is just a side, and we could actually use, we could prove this in general. This is the way you would prove the formula for the volume of the sphere. You might recall you never proved it before, but you always knew that the volume of a sphere was 4/3 pi r cubed. And for our case, r is 3. So that's 27, 3 goes in 27, 9, that's 36 pi. That would be an entire sphere, right? So the entire volume of that sphere is 36 pi, but notice we only took half of it, top half, which obviously is 18 pi. So kind of cool to see that, and if you wanted to, you really could prove this in general. Just call the x squared plus y squared plus z squared r squared, and take the whole sphere, if you like. There you'd have to go from the top half to the bottom half, so you'd have to have a plus or minus, so it gets a little bit more detailed, but you could prove it, so it's kind of cool. Alright, so that's the end of that lesson, but something very important. In the homework and handouts of exam 4 folder, there is a document that's 6 pages long, and it says match the solid with the integral. So each page has sketches numbered with Arabic numerals and corresponding lettered integrals. So you want to tell me which integral goes with which sketch. So, you know, here's a real easy one. 0 to 1, 0 to 1 in the x and y. Looks like number 2 is a immediately, right? But you could finish up the rest. So this has 6 pages, all different sketches. So the first one 2-dimensional, second one 3-dimensional, rectangular, third page some 3-dimensional with circle stuff, or 2-dimensional with circle stuff, and so on. You can see the last pages 4, 5, and 6 are polar. 4 is polar, 5 is cylindrical, and page 6 is spherical. Okay, so this little problem set here of matching the solid with the integral, this is going to be due with the final exam. This is going to be part of your final exam. I'll make some announcements trying to make that clear, but this is going to be part of the final exam. So it's 30 points because there's 30 questions. Each page is separate. Each page, integrals on each page belong to the corresponding graphs on those pages, respective pages. And so it's going to be worth 30 points, and you'll see some similar ones in the notes. The fun ones are at the end, right, where we, the spherical and cylindrical, and you'll find some similar examples, so match them up with some of the things we did, and they'll be very similar. So this is 30 points of the final exam, and the final exams were 200 points. Check your announcements and Blackboard and your T-Wolves email. Just remember that this needs to be turned in as 30 points for the final exam out of the 200. Alright, so that's the end of the material for exam 4. It's actually a designed take-home exam. So check your T-Wolves email and Blackboard, and should have it posted soon.